Hello everyone. So today we have the Chapter 5 quiz review, sections 5.1 to 5.3. So the first problem here, 4e to the negative 8x power, all taken to the fifth power. We need to simplify it. So we have the 4 and the e is being multiplied. So that 4 is a separate factor, which means we need to take the 4 and the e to the negative 8x power to the fifth power. So we're raising both of them to the fifth power. So when we do that, 4 to the fifth power, we simplify that, and then the e to the negative 8x power we have to take to the fifth power. So your exponent rules, when you take the 4 to the fifth power, you get 1024, but exponent rules, you multiply those exponents when you have an exponent outside of an exponent, which gives you negative 40x. And that is your simplified answer for number 1. Moving on to number 2. So in number 2, we have the same base. So whenever you have the same base and you're multiplying, you add the exponents. So when I add the 9 and the negative 6, I just get 3. And that's all we can do to simplify it. Number 3, we have start out with 32 over e to the 8th over 4e to the 3rd. So your coefficients in front we're going to reduce. So in this case, the 8 and the 4 can both be divided by 4, which gives you 8. And I even showed the factors here. So 32 factors into 4 and 8. 4 is the common factor, so those can be reduced. And then my e to the 8th, I can factor into e to the 3rd and e to the 5th. So the e to the 3rd is what they have in common. So you're left with 8 e to the 5th once you've simplified. And that's it for that one. And I think there's one more here. Number 4, going through this step by step. So we have a cubed root. So anything that's being multiplied, so the 27 and the e, you can separate. Again, this is one of your radical rules, that you can separate the factors of the radicand. So I can separate the cubed root and take the cubed root of 27 separately from the cubed root of e to the 12x power. So the cubed root of 27 gives me 3. That's a whole number now. And then I rewrote the power over the root so that you can see that when you divide, you get 4x. You didn't know, I mean, you could just divide here 12x by 3, which gives you 4x. So, but sometimes it's helpful to rewrite things in rational form so that we can see how that simplifies. So 3e to the 4x power. All right, moving on now to our story problem here. We're investing $17,000 or $1,700 in an account earning 8% annual interest. It's compounded continuously. So we have to write an exponential function for a that is in the account after t years. So the first thing we're doing is just writing the function. So your formula that you do need to know, this will not be given to you, is a equals p times e to the r times t power. So the principal amount is the starting amount is 1,700. Your rate, that's 8%. You have to change it to a decimal, so divide by 100 gives you 0.08. So that's going to go now into your exponent for r. And that is now our equation. So a is what we're trying to is what the equation equals, and then 1,700 is your principal, e is part of the formula, replace your r, and your t is still your variable there. So now we get to part B. In part B, they got a little bit of work here. Oh, I didn't actually calculate that out, so I'll have to do that. Okay, so basically what they're asking in part B is when will the balance be at least $5,000? So if we want our balance to be at least $5,000, we want that amount to be greater than or equal to 5,000. Well, what does A equal? It equals this expression here. So if I replace my A with the equation that equals A, and then solve for t. So I would divide by the 1700, which gives me, I'm going to leave this as a simplified fraction, 50 over 17. And then now I've got my e and my exponent isolated. So then we can solve or eliminate the e by taking the natural log of both sides of the equation. So the natural log and the e undo each other, which brings the exponent out of the exponent, and we get 0.08t greater than or equal to the natural log of 50 over 17, and then divide both sides by the 0.8. So this is where I would now put it in the calculator now that I've isolated my variable. So take my natural log of 50 divided by 17. I'm going to close the parentheses there and then divide that by 0.08. And I will round it to the nearest tenth of a year, which will give me 13.5 years. So I need to be investing that money for at least 13.5 years if I want to have at least $5,000. All right, moving on. So the next equation we have is A equals, so they're giving you the equation and they're telling you this is the amount in your account, and then you are given a graph that represents your sister's amount. And there are two questions: which account had the greater principal, and then which one will have more after 10 years. So looking at your equation, you should recognize that the $3,200 is the principal amount in your account. And from the graph, you should recognize that the y-intercept is the starting or principal amount in your sister's account. So if we answer the first question, who has more in their account to begin with? You do. So your account has more for the principal amount. But then when we compare after 10 years, so in 10 years, if we use the graph, go from 10 up to the graph and over and estimate, that's approximately, I estimated it to be about $5,800 is what your sister would have after 10 years. But in order to figure out what you would have to have in your account after 10 years, you need to put 10 in for your time. So multiply that 0.05 times 10 and then put that whole thing in the calculator. So whether you call it your account or my account, as long as you understand. So we have the 10 now in here for x, or for t, and we just plug that in our calculator and we get $5,276 is what we would have in our account after 10 years. So I put a sub 10 because 10 is what I'm substituting into the equation. So the answer to the first question then would be my account has a greater principal amount. However, my sister has a greater amount after 10 years because in the graph it looks like, let me just zoom out here so you can see both things at the same time. So it looks like she's got about 5,800. She's almost at 6,000, where you are closer to 5,000. So there's a big difference there. So definitely your sister has more after 10 years. All right, moving on, second page. All right, so in this set of problems, we are rewriting the equations in logarithmic form. So you need to know these basic principles. So in an exponential, when you have an exponential equation, your base is taken to the power of x equals y. So if b to the x power equals y, and I call that the base, the exponent, and the term. In logarithmic form, this equation is written as log base b, so whatever this number is goes down here, whatever your term is goes in the place for the term, and then the exponent is what goes after the equals. So your log will always equal the exponent. So if you remember the log equals the exponent, then when you set up your log, that exponent goes after the equals. Your base is still the same, but it becomes little, and then that is your term. Make sure that the way you write this is correct. So this 10 should be small and down by this g. This term here should be the same size as the log, so standard size, and so should the negative 3. Here's another example of rewriting in logarithmic form. So again, the exponent is what goes after the equals. The base is your 16, and then 8 is your term. The next one, we have our exponent, negative 2, goes after the equals. Your base is 1 over 49, again, that's down there, and your term is 7. So hopefully these are easy ones for you. The next set of problems, you are rewriting them, the equations from logarithmic form to exponential form. So this is your base, this is your exponent, the 1 is your term. So when we rewrite it, that 0 becomes the exponent of our base, which is 3, and it equals 1. When you do rewrite these, make sure that they make sense. Does 3 to the 0 power equal 1? Yes. So that does work. So that is the correct answer. Your base, 1/3, becomes a regular size number. Your exponent, negative 1, goes here, and then your term goes there. And does 1/3 to the negative first power equal 3? Yes, because when you take some to the negative first power, it basically flips the fraction, which makes it 3. All right, and then the last one, your base is 125, your exponent is 1/3, and it equals the term. And check, does 125 to the 1/3 power equal 5? Yes, it is the cubed root. So 1/3 power is the same as a cubed root, and the cubed root of 125 is 5. All right, the next page here. So we evaluate now without a calculator. So I'm not going to take your calculator away for one problem, but you should be able to do these without the calculator. So if you don't have to necessarily set this equal to x, you could just ask yourself 10 to what power would equal 0.001. So if you know, if you understand the exponents well, you would know that that would be negative 3. But if you need to, you can set this equal to x and then rewrite it in exponential form and ask it that way. So 10 to what power would equal 0.001? Negative 3. The next one you have is 1/3 is your base and 81 is your term. So in your head you can think, well, 1/3 to what power is 81? Well, I know that 3 to the 4th power is 81. So if I have to make this fraction a whole number, I have to have a negative exponent so that I can take the reciprocal of that. So again, you can set it equal to x and then rewrite it in exponential form, and then think of it that way. So another thing that I just thought of is you might find it helpful to rewrite these things with the same base. So both of them are powers of 3. So let me just kind of show you what that would look like. So if I were to rewrite 1/3 as a power of 3, I need a little bit more room here. And this may help in the last problem. So I know that 3 to the negative first power is 1/3. And then if I take that to the x power and I multiply those exponents together, I would get 3 to the negative 1x. And then I know that 81 is 3 to the 4th power. So once you have the same base, you can set your exponents equal to each other. So the negative 1x would equal 4. And then if you divide by negative 1, again, you would get x equals negative 4. So that's another way of, if that helps, to try to get the same base. And that actually will be something we'll need to do when we start solving more difficult equations. All right, the next one here, again, you're finding the log base 25 of 5. So 25, if you set this equal to x and then rewrite it in exponential form, you're trying to figure out 25 to what power equals 5. And again, we could rewrite this as, let me use the green pen. You could rewrite this as 5 squared to the x power. So 25 is 5 squared to the x power equals 5 to the first power. And then your exponent outside of an exponent, 5 to the 2x power equals 5 to the first. So once you've got the same exponent, you can set those exponents equal to each other, and so if the 2x equals 1, divide by 2 and you would get 1/2. But also if you realize that 5 is the square root of 25, and 1/2, the power of 1/2 is the same as a square root. So that's another way to think of it. All right, needed more room there. And then this last one, 7 and then 343. If you know your powers, you know that 7 to the third power equals 343. But again, I've set it equal to x and then rewrote it in exponential form, and then x equals 3 because 7 to the third power is 343. Okay, the next set of problems. Now we are simplifying, and one of the things that you need to know are these rules that when you have a base and an exponent that has a log with the same base, that though the base and the log base b undo each other, which equals x, or whatever is in that exponent. If you have a logarithmic equation with a base and then the term has that same base, they would eliminate each other and you get whatever the exponent, it would equal whatever the exponent is. So we've got a few cases like this. So your e is your base, your natural log is e to the base, or log base e. So those are they are opposite operations, so they undo each other, which then would just leave you with a value of 14, and that's it. The second example here, we've got a 10, which is our base, and then we have a log with no base. Well, you've got to understand that when there's no base written, the unwritten base is 10. So that base of 10 and that log, which has a base of 10, would undo each other, which gives you 14 again. This next one here, you've got a log base 9, and that base is 9 in the term, so they undo each other, which gives you x. Now this last one is a little bit tricky because we don't have the same base in the log and in the term. So what you want to do is rewrite this 8 as a power of 2. So if I rewrite the 8 as 2 to the third power and then multiply my exponents together, I will get log base 2 of 2 to the 3x power. So that log base 2 and that 2 undo each other, which then simplifies to just 3x. So if your bases are not the same, if the base here does not match the base of the exponent, then rewrite the base to be the same, if you can. All right, and then the next ones here, you're just plugging it in the calculator. So you're rounding it to 3 decimal places. So your log of 7 in your calculator, you just push log and 7, hit equals, and round correctly, and you get 0.845. This one should be a negative 0.105, but this is a natural log, so you use the ln button, not the log button. And then for the next one, you would use the log button again of 2.3, which is approximately 0.3262. And then the last one, the natural log of 5, so just plug that in the calculator, hit equals, and round correctly. All right, so for the next couple problems, we are finding the inverse of a function. So what you could do, if you know that if f of x equals b to the x power, or y equals b to the x power, its inverse has to be a log function. So an exponential function always has an inverse that's a log function. A log function always has an inverse that's the exponential function, and they have the same base. So if all you have is the base to the power of x, then your inverse is going to be a log with that same base and a term of x. So if you know that, you can kind of shortcut some of these couple of problems, 25 and 26. So if this is exponential, then I know my inverse is going to be a log with the same base of x. If this is a logarithmic function, then I know my inverse will be an exponential function with a 3 to the x power. But if you forget, or if you have something more complicated, then you do need to follow the steps like you've done before to find inverse functions, and that is to switch your x and y, and then we want to solve for y. Well, to get rid of a base, we need a log with the same base. So we're going to take the log base 7 of both sides of the equation, and then bring that x down and that 7 to the y power. Now that log base 7 and that 7 undo each other and brings that y out of the exponent. So now you have the y by itself, and that is your inverse equation. So y equals log base 7 of x is the inverse of y equals 7 to the x power. But again, you can notice they have the same base. If the exponent, the x is the exponent in your exponential, x is the term in its inverse in the log function. Okay, so this next one, again, we want to switch the x and the y, and then we want to get rid of a log base 3, or undo log base 3. Well, the way you undo a log base 3 is with a base. So if I raise both sides of the equation to the exponent and make this 3, so basically when I rewrote this, think of this as 3 to the x power and 3 to the power of log base 3 of y. So that 3 and log base 3 will undo each other, which gives you the y then by itself to the 3 and equals 3 to the x power. So y equals 3 to the x power is your inverse. Okay, and then the last problem where we're finding the inverse. This one you do have to do a little bit more work. You can't use the shortcut here. So switch your x and y, which will give you x equals y, e to the y power minus 2. You have to get the base and the exponent by itself. So you do need to add 2 next, which will then make this a binomial over here. To get rid of a base, you need a log with the same base. Well, the log that has the same base as e is ln, which is log base e. But you have to do that to both sides. So you're taking the natural log of the whole x plus 2, that has to be in parentheses, and the natural log of e to the y. So those cancel out or undo each other, giving you the y by itself, which then gives you your inverse. Y equals the natural log of x plus 2. And there we have it. I think we have a few more inverse problems that are, a couple more that are a little bit more involved. So again, step number 1, we want to switch the x and y. So this becomes x, this becomes y. To get rid of a log, we need to exponentialize the equation. So we need to raise both sides of the equation into the exponent. And we need a base of e, because that's the base of the natural log. So I just put the e here, made it look like this was the exponent, and then put the e here, made it look like that was the exponent. So then I can cancel those out, or they undo each other, and now I have e to the x power equals y plus 5. And then from there, to get the y by itself, just subtract your 5, which gives you e to the x power minus 5 equals y. And then when we switch it around, so the y goes first, y equals e to the x power minus 5. All right, then we have our next problem here. This one's a little bit more complicated. Also, so step number 1, switch your x and y. So x equals 1/4 log base 2 of y minus 3. Then we need to get the log base and term, so we need to get this all by itself. So we need to undo that 1/4 that's being multiplied. So we can do that by multiplying by its reciprocal, 4. So if I multiply both sides of the equation by 4, I will get 4x on the left, and then the 4 and the 1/4 cancel each or become 1, which we don't have to put 1 in front. And then we have our log base 2 of y minus 3. Then again, to get rid of a log, we need to raise the log to the exponent or exponentialize it and put a base of 2. Because our base is 2 here, we need to have a base of 2 here. So this side becomes 2 to the power of 4x, and this side becomes 2 to the power of log base 2 of y minus 3. So that base and that log base 2 undo each other, which will give us y minus 3 on the right and 2 to the 4x power on the left. And then last step, add your 3, and you get y equals 2 to the 4x power plus 3 as your inverse. Okay, moving on. So the next problem that we have, we are writing rules. So we're writing a rule g, so your final answer should say g of x equals. This is our starting function, f of x equals 4 to the x power. The first thing we're going to do is reflect it in the y-axis, which affects the x-coordinate. So anytime you have something that affects the x-coordinate, you need to replace the x with something else. Well, if we're reflecting in the y-axis, we replace the x with a negative 1x. So that x becomes negative 1x and looks like this. So this is after my step 1, my 4 to the x power becomes 4 to the negative 1x power. And then step 2, I have a translation 4 units to the right. So again, that's something that affects the x coordinates. So I replace the x now with x minus 4. So this x that I had from step 1 needs to be replaced with x minus 4. So that does need to be in parentheses, and you can leave it as negative 1 parentheses x minus 4. You can leave your answer like that. I think I have that right here. Yeah, so this is an acceptable answer, but if you distribute the negative, make sure you do it properly. So if you distribute that negative, it would be negative x plus 4 in the exponent, because the negative would change that 4 to a positive. All right, the next one we have, we are starting with a logarithmic function. The base is 1/9 and x is our term. We're going to translate it 8 units to the right. So again, going to the right affects the x. So whenever you affects the x, you replace the x with x minus 4. So that x becomes x minus 4, but the base is still 1/9. Then our next step is it says followed by a vertical stretch by a factor of 5, which means we need to multiply the whole function by 5. Now, some people might think, well, don't I distribute the 5 to in front here and there? No. That log, base, and term represents one whole term. That's like one number. So when you're multiplying this by 5, it just goes in, it's 5 times this whole thing. Now, had there been a plus or minus a number at the end, then the 5 would have to be multiplied by something else at the end. If there was a k value or a vertical translation up or down, that would affect this number at the end. But we don't have that, so it's just 5. Make sure you have g of x equals in front of it, 5 log base 1/9 of x minus 4. All right, so the next one we have is another exponential function. We are going to reflect this one over the in the x-axis now. So basically that means we want to multiply by negative 1. So when I multiply this 8 to the x power by negative 1, it's just, you can simplify it to negative 8 to the x power. But keep in mind that that negative is not being taken to the power unless it was in parentheses. So we don't want to put it in parentheses. We want to make sure it's not in parentheses. So this means the 8 is being taken to the x power, and it's being multiplied by negative 1 at the end. All right, then we have followed by a translation 3 units down. So we're just going to subtract 3 at the end. So once we've done that, put a minus 3 on the end, and that's it. So write your final answer. Always make sure you put g of x equals, and negative 8 to the x power minus 3 would be your answer there. All right, and then number 33, we have log base 1/2 of x. We are translating it 8 units up, so we're simply going to add 8 to the end. So that's what we have after step 1. Then in step 2, we have a horizontal shrink by a factor of 1/8. So whenever we have a horizontal stretch or shrink, we have to take the reciprocal or of this 1/8, which is 8. And again, it's going to affect the x, so we replace the x with 8x. So this x here, everything else stays the same. The log, the base, just the x gets changed to 8x. And then you still have that plus 8 at the end. And that was the last thing that we were doing. So your final answer, g of x equals log base 1/2 of 8x, that needs to be in parentheses, and then plus 8. The last one on this page, now we're describing the transformations. So they're giving us the starting function and the ending function. So make sure you look at the starting function very carefully and see what's changing. You only describe the things that are changing. So the base is staying the same. The base is not a transformation. The x, though, becomes x plus 2. So what would do that? A horizontal translation to the left 2. And then the minus 3 represents a vertical translation down 3. The next problem here, this one's a little bit tricky because you have to state the followed by. But let's start at the beginning. Look at what you're given. Look at what you have now. So the base doesn't change. The x, though, becomes 4x minus 1. So some students might want to think that it's going to be a horizontal shrink by a factor of 1/4 and then a horizontal translation to the right one. But if you do that in that order, that would not give you 4x minus 1. So you have to do the horizontal translation to the right first, and then followed by a horizontal shrink by a factor of 1/4, because you want to replace. So I think I have it down here. Yeah. So you want to make that replace that x with x minus 1 first, then replace the x with 4x. If you were to do the horizontal shrink by a factor of 1/4 first, if you had changed the x to 4x first and then did a horizontal translation to the right 4, it would have looked like 0.3 to the 4 parentheses x minus 1. So if that 4 was outside of the parentheses, then it you could call it a shrink followed by a horizontal translation to the right one. But if you were to do that, if you were to distribute that, you would see that that is not the same as 4x minus 1. This would be equivalent to 4x minus 4. So those are not equal. Okay, so hopefully that made sense. If not, come see me and I'll try to explain it again. All right, last page. So we have, look at what you're starting with, look at what you have right now. So the e to the x power is still e to the x power. Nothing is happening with the x, which means there's nothing horizontal going on. The negative and the 2 are two different transformations. The negative represents a reflection over the x-axis or in the x-axis. The 2 is your vertical stretch by a factor of 2, and the plus 5 at the end is a vertical translation up 5. And then 37 here, again, look at your base. It does not change. The base doesn't do anything. That's not any type of transformation. So the only thing that's changing is the 3/4 in front. Because it's between 0 and 1, it's a vertical shrink by a factor of 3/4. The negative is now on the inside with the x, which means it's a reflection over the y-axis, not the x-axis. And then that 2 is on the inside, so we have to remember to take the reciprocal of that, which is 1/2. And 1/2 is between 0 and 1, so that means it's a horizontal shrink by a factor of 1/2. We have more. Okay. So again, look at what we have to begin with and look at what we have now. So this is kind of like that other problem where you have to describe the -2 first. So you have to perform the horizontal translation 2 units to the right first, then followed by the horizontal shrink by a factor of 1/3. And I think nope, I don't have that down there. So off to the side. So if I were to replace the x with the x minus 2 first, and then replace the x with the 3x, that minus 2 is not affected. So that works if you know, with the horizontal translation to the right 2, and then the horizontal shrink by a factor of 1/3, or so that would replace there. If you do it the other way around, so again, let's say we start with x. If we do it the other way around and we say that it's a horizontal shrink by a factor of 1/3 first, that would make this a 3x first, and then if you do the horizontal translation to the right 2, you would replace that x with x minus 2 in parentheses, which would give us 3x minus 6. So this does not equal that. So they are not equal. So you have to do the translation before you do the horizontal shrink. All right, one more. So here, this is what we're starting with. Again, the base did not change, but the x became 1/2 x. So again, when we have something on the inside that's being multiplied, take the reciprocal of it, that's 2. So 2 is bigger than 1, which means it's a horizontal stretch by a factor of 2. And that minus 4 at the end is a vertical translation down 4. Now we have a couple of graphs. So the first thing we're going to graph is the log base 1/3 of x, and then we're going to graph its inverse, write the inverse, and then state the domain for the inverse of the, so you're stating the inverse domain. Okay, so what do we have here? So this is a logarithmic function. Your base is 1/3. So when I'm making my table, I am going to use the inverse. I like to go in this order. You don't have to go in this order, but I take the inverse of my base, so the reciprocal of the reciprocal of my base, which is 3. That's what I'll plug in first, and then the base so these are basically my y values. The other way I had described it is if you set this equal to the equation equal to y. So if you say log base 1/3 of x equals y, if you can see that, and then I rewrite this in exponential form, I would have 1/3 to the y power equals x. So 1/3 to the y power equals x. So if you want, you could put the -1, 0, and 1 in place of your y values, and then take them to the power to get the x values. Either way, you're going to get 3, -1, 1, 0, and 1/3 1. So I always use the reciprocal of the base, 1, and the base itself. Or rewrite it and then put your -1, 0, 1 on the right. 1/3 to the negative first power is 3. And then plugging in 0 for y, 1/3 to the 0 power gives us an x value of 1. 1/3 to the first power gives us an x value of 1/3. So those are the 3 points that I'm going to graph for my logarithmic function. So the 3, -1, 1, 0, 1/3, 1. Don't forget that there is a vertical asymptote of x equals 0, so you should not cross that y-axis. And so that's the graph of log base 1/3 of x. If I want to graph its inverse, I could just flip my x and y coordinates, which will give me -1, 0, 1 for my x values, and 3, 1, 1/3 for my y values. When I graph those 3 points, the -1, 3 is here, 0, 1, and 1, 1/3. But the inverse of a log is an exponential function, which means it's going to have a horizontal asymptote. Since the vertical asymptote of the log was x equals 0, the horizontal asymptote for its inverse will be y equals 0, which means that graph cannot cross the x-axis. And then to write the inverse, if I just use that rule, that I know that the inverse of a log is exponential, it's going to be 1/3 for the base, and then my x becomes my exponent. So that is my inverse, and the exponential function has a domain of all real numbers. And then for fun, I always put the line of reflection in there to show that they are symmetrical. And then the last problem, the last graph here, now we have an exponential function. So 5 to the x power. If I were to graph, I would plug in negative 1, 0, and 1. So 5 to the negative first power is 1/5. 5 to the 0 power is 1, and 5 to the first power is 5. So that gives me this graph, and it has a horizontal asymptote of y equals 0. Since this is an exponential function, the inverse is a logarithmic function. And instead of having a horizontal asymptote of y equals 0, I'm going to have a vertical asymptote of x equals 0. And then again, if I take my table and flip my points, I would have 1/5. So the negative 1, 0, 1 would become my y values. 1/5, 1, and 5 become my x values. So that when I graph it, 1/5, you're just going to go a smidgen to the right and then down 1. 1, 0 is right here, and then 5, 1 is right there. So connect them, make it curve, and get closer. Looks like it's merging in with that y-axis there. And then the inverse is going to be a log with the same base, but your x is going to be your term. Now the domain of a log, is always either greater than or less than it's always x greater than or less than whatever the vertical asymptote is. So if our vertical asymptote is at 0 and it's to the right, our domain is going to be x greater than 0. It cannot equal it though. So make sure you do not put an equal sign there. All right, so that is the end of the review. Good luck on your quiz.